Still going. So I tried to listen to
these four kids. And he said, and I said, man, there's one he said, oh, do that. I come from very good. Very
Only once a year.
well, I mean, it's not healthy. That's a couple of places.
But it's okay.
Yeah, but the entire sky is you don't have to see
Just leave it, it's
So how often?
Great night on the jelly the other night, about a week ago. And Yuri did it about 30 times with one. I couldn't believe it. C was 0.5.
Can you hear me? Yeah, well, welcome to this third installation of the CFA Colloquium Series for the fall of 24. My name's Charlie Latta, and I am your host today, which basically means I get the honor and privilege to introduce our speaker, who is here, Professor Ralf Klessen, who's visiting us from the University of Heidelberg. And he's a very distinguished astrophysicist, so I'll give you some of his background here. He did his graduate work at MPI Heidelberg and the University of Heidelberg, and way back in 1998 got his PhD at the University of Heidelberg. He then went on to postdocs at Leiden in Holland and Santa Cruz, UC Santa Cruz. And in 2002, he moved to the Astrophysical Institute, Potsdam, where he developed and was head of an Emmy Noether research group in the theory of star formation. Since 2006, he's been at the University of Heidelberg, where among many other things he's done there, he was served as Dean of Study in Physics and Astronomy. Currently, Ralf is visiting Cambridge as a fellow of the Radcliffe Institute for the 24-25 academic year. So, welcome, Ralf. Not yet? Not finished? Since his grad school days, his primary research interest has been in the theory of star formation. He has more than 500 published papers, which have accumulated thousands upon thousands of citations. He is perhaps best known for his work on the role of turbulence in star formation, but he's really worked on all aspects of the subject, from the present-day star formation in the local Milky Way to the formation of the very first stars at the edge of the universe, a subject he's going to discuss with us today. He is widely recognized as an expert on this particular field, as evidenced by his annual review article that he wrote with Simon Glover on this subject that appears in the most recent ANA volume. Now, study of the origin of the first stars has attracted a lot of theoretical interest, as we all know. Today, we're about to hear about some extraordinary inferences that have come out of the theoretical study of the first stars, including the hypothesized existence of hydrogen-burning stars or star-like objects with masses that rival entire globular clusters and giant molecular clouds, objects which may be the precursors of massive black holes, supermassive black holes. This is fantastic to me, fantastic and kind of strange stuff, and it brings to my mind some prescient intuition that a British biologist named J.B.S. Haldane wrote more than a century ago. And what he said, quote, is that the universe is not only queerer than we suppose, but is queerer than we can suppose. So now I'll turn the podium over to Ralf, and I'm really looking forward to hearing about the remarkable going-ons in the earliest epochs of cosmic history.
He doesn't need it.
Can you hear me? First question is always. No. All right. First failure of my talk. Now. All right. Is it better now? Oh, it disappeared. All right. Here we go. All right, Charlie, many thanks for this fantastic introduction. And the quote I was not aware of, but I fully agree. I think there's just so much more stuff out there than we can possibly imagine, and that immediately leads to another quote: there are known unknowns and unknown unknowns and things we have no idea about. I'm here for a year. I'm super happy. I will split my time between this institute here and the Radcliffe Institute for Advanced Studies, where I just came from one of the talks, noontime talks. And so I try to do my best to both entertain you and hopefully tell you hardcore astrophysics about what we know about the first stars in the universe. And I should say that, you know, I try not to boast or pretend that there are too many things we know. I think it's much more interesting to talk about things we do not know. And in this vein, if you have any questions, please do not wait until the end and you have forgotten the question. Just let me know as we go along. So as Charlie has mentioned, I try to give you a brief overview of the current knowledge and the open questions concerning the first stars in the universe, how they formed, what their potential properties are, and how they may possibly have shaped the subsequent evolution of the universe. I start with some theory, then I talk about what we call nowadays the standard pathway of population 3 star formation. I digress a bit into the more standard pathway of star formation as we see in the Milky Way today. Then I talk about one of my favorite subjects, supermassive stars. And as a preview, these guys can probably have several 100,000, up to 1 million or more solar masses during the hydrogen burning phase. And I try to argue why this could possibly be the case and where to find them. And then there is a tiny little postscriptum about how we can test all that stuff. And this postscriptum is very tiny, as you can tell, this is a very speculative still in many parts, part of astrophysical theory. So I will base this talk largely on the review that Simon Glover and myself put out last year. And you find more details in that. But I try to give you stuff that has developed since and go beyond of the restricted constraints we had in terms of space and also references and so on. So, as usual in this talk, just a context. The evolution of the universe, we have seen this gazillions of times. Charlie, you have, I think, also shown it in your talk 2 weeks ago. And so this is where we are. This is inflation. These are the so-called dark ages when the cosmic microwave background has, shifted through the optical into the microwave background and has been essentially invisible to the eye. And because there were no sources emitting light, these were called the dark ages. And so these first stars are essentially the first luminous objects that could potentially be visible to our eye. And so one of the quests is with James Webb and other detectors to find evidence for their existence. And so this is more or less the context where I place this talk into. So a few million years after the Big Bang, what conditions do we need to form the first stars in our universe? And so the key question is, of course, to start with, what are actually the criteria for star formation? So as you know, the universe is dominated by dark matter, and the gas just is along the right, at least initially. So the first criterion is that the dark matter halos need to decouple from the expansion of the universe by their own gravity and start to contract. And so gas comes along, but you need to go into a runaway collapse that proceeds to stellar densities. And so there are two key criterion that needs to be met. First is that the gravitational time scale needs to be smaller than the sound crossing time, or that the potential energy dominates over all opposing forces. This goes back to James Jeans at the early 20th century. 1902 was his seminal paper on this. But there is one more, because as the gas gets compressed, it heats up. And so it needs to get rid of these excess energy, so there is a cooling time scale involved, and that is the Ries-Ostraker criterion. So the cooling time scale needs to be shorter than the dynamical time scales indicated up here. And so that leads you immediately to the physics we need to involve. We need to look at the competition between the various heating and cooling processes, and so we need to understand primordial chemistry. So then the super simple picture is that the dark matter potential starts to decouple, go into collapse, gas flows in, it decouples and goes into runaway collapse, and eventually we have the first stars. But we have these two criteria, and so following the original analysis of James Jeans, who asked the question, if I have a self-gravitating blob of gas and I have just gas pressure, what is the critical mass for collapse? And it turns out that this scales inversely proportional to the square root of the density. The denser the gas is, the more likely gravity wins. And it goes with the temperature to the third power, or the sound speed with, the temperature to the 3/2 power, or the sound speed to the third power. So the hotter it is, the more difficult it is for gravity. And we can put this into a cosmological context, and there are people at this institute who have contributed greatly to this discussion. But there's this other criterion, the one about the chemistry. And it turns out that there isn't much chemistry going on. We have hydrogen, we have helium, which is chemically inert largely, and we have not much else. So in this context, we need to look for molecular hydrogen, which has a forbidden transition that can, once collisionally excited, get rid of the energy in a radiative fashion and hence cools the gas, takes it out of the kinetic sector and puts it into the radiative sector. And this brings you down to maybe temperatures of 500 Kelvin if you allow for a proper dipole moment. So if you consider that hydrogen not only has one proton, but sometimes it can also have a neutron, then you have suddenly a dipole moment, a tiny one. Then you can go down a bit further. So the key question for the chemistry is, how can we form H2? We know at present days this happens as the surfaces of fractal dust grains. None of that exists in the primordial universe, so you have to go through the gas phase chemistry. And in principle, we need 3 electrons as catalyst, and then we can either go to this thing, or we have an H+ pathway, etc., etc. And there exists another pathway at very high densities, and we can formulate that into, again, a critical masses function, of redshift, and it can be in the most simple form described like that. Reality is more complex, there's more physics involved, but this is what the most simple approach piece of paper approach kind of would give you. So a chemical network would roughly look like this. You see lots of H business. You see a bit of plus and E minus and not much else. So that is not so difficult to put onto a computer, and so most respectable primordial star formation calculations have a chemical network that runs alongside the hydrodynamics. And if you do that, and I have picked here work that is from Louis Prohl, you find roughly this evolution in the log temperature, log density plot, which covers quite some order in scales and also in temporal scales, which are not depicted here. So typically, the evolution starts here, and then as the halo contracts, the density goes up. We talk about collisional processes, and so they go quadratic with the density, and so the gas, quite counterintuitively, starts to cool. It goes down here, and it comes to roughly a few hundred Kelvin, because this is what you can reach with cooling with molecular hydrogen. As one region of the universe compresses, another one goes into adiabatic expansion, and this is realized here to the left-hand side. So the gas then loiters here for a while until it has accumulated enough material. Then it continues along this path. Eventually, three-body H2 formation sets in. The gas becomes optically thick to its own radiation. Eventually, so the temperature goes up, up, up. Eventually, you can collisionally de-excite the molecular hydrogen, and that happens roughly here. And this is the result of a time-dependent chemical network, and you see there is some mismatch between the chemical and the dynamical timescales here, whereas here we have reached more or less chemical equilibrium. So we can compare then the heating and cooling functions for the primordial gas with the present-day chemistry, and you see it has C and O and C plus and dust and cosmic rays and all that stuff. The primordial one is much simpler, as I said. Essentially, we have the competition of the PDV heat and various forms of cooling. This is the collision-induced emission of hydrogen, which is quite cool. If you have enough density, then it could be that a hydrogen molecule comes by another hydrogen molecule via van der Waals interaction, excites a temporary dipole, and now you have the dipole emission at your disposal, and which is much more efficient than the actual forbidden transition of the molecule under its normal conditions. So there's also interesting molecular physics involved actually in these heating and cooling processes. You can realize then this on a computer, and this is a model from Kazu Omukai here at the top. And let me just zoom into this model, where he plots equilibrium chemistry, a one-zone chemical model, exposed to different compressions, assuming there's some kind of collapse going on, and he's doing this for different metallicities. So taking in part some of these more complex heating and cooling functions into account. So if you do that, you notice several things in this Omukai plot, which to me I think is the plot towards understanding how star formation works on a very fundamental level. So again, we are scanning many orders of magnitude in density and quite some orders of magnitude in temperature. And we notice that the effective equation of state, so this is just a reflection of the effective equation of state. How does density and temperature relate and relate to pressure? So we talk about an effective equation of state, and we notice that there is something like a forbidden region where if you compress the gas further, suddenly the temperature goes up. And that has to do with the gas becoming opaque to the thermal radiation. So this is all done via lines, but once it's in the thermal infrared, photons are gone. Here they are absorbed by the neighboring photons. We can place the critical mass for gravitational collapse according to the simple Jeans picture on these plots. And we notice that, we have one solar mass here, we have roughly a Jupiter mass here, and we have roughly 100 solar masses here. And I should tell you what the different curves are. Red is primordial gas, and then this is more or less the present-day universe. Do not worry about the details of the chemistry. This is limited kind of by the cosmic microwave background. So let me start now with primordial gas. And the first thing you notice is that whereas the present-day gas has these dips and dimples, it has structure in its effective equation of state, this is not really the case for the primordial gas. You can simply assume it is almost isothermal with an adiabatic index of 1.0 something, 07 or something like that. I have the number here. Over 10 decades in density. However, the gas only heats up from a few hundred Kelvin to maybe 2000 Kelvin. So again, not even a decade in temperature, but many decades in density. And so this has implications for fragmentation, and we need to discuss that. So it turns out that the primordial gas always has some angular momentum, and so as it collapses towards the center of the halo, in the most simple picture, it also builds up an accretionally dominated disk, very much like star formation at present days, planet formation in this disk. And for many years, it has been thought, based on maybe not quite the right chemistry and some assumptions not quite right, that this disk is unstable against fragmentation. But this is not the case. If you do it right, if you really follow into the fragmentation, then you see that after you have reached enormous density contrasts, you build an accretion disk because the mass load onto these disks is larger than its ability to transport the material inwards by viscous transport processes. It becomes unstable, forms spiral arms. These start to self-interact, and voila, you have a second fragment, a third fragment, etc., etc. You can put that into more details on a computer. This is work by Thomas Greif, who also was here a while ago. And you see the dynamics involved. On the left-hand side, we show the temperature, and here the density. And so lots of dynamics. And you should have a look at this thing. This is 11.4 years. As I said, this is 15 years ago. We can do better now. We can reach a few hundred years. But given the fact that star formation lasts in this context over 100,000 years, it is clear that we get the initial phase of fragmentation right, but then there's a huge gap in our understanding, and then we assume maybe we have formed stars, maybe we have formed massive stars that produce copious amounts of ionizing photons. What would they do with the environment? But to really scan the full formation process, including feedback, magnetic fields, dark matter annihilation, cosmic streaming velocities, all that stuff has never been done. All right. So this was work that we have done, and I try to show you this and other more recent works to see that there's a certain picture that crystallizes out of this. These are several of these calculations, and they roughly show a relatively flat mass spectrum, starting at subsolar masses and ending at a few solar masses. And the upper mass simply was given by the fact that we had to stop. The calculations became too costly. So Louis Prohl continued a bit further. So instead of 2 digits numbers, we have now 3 digits. All right, improvement. This is work by Wollenberg. This is work by Hirano. And I have compiled it together in the review essentially to this figure, which goes from hundreds of a solar mass. So a Jupiter brown dwarf thing up to a few hundred solar masses. And this is the cumulative mass spectrum, and these differ greatly in terms of resolution. They differ greatly in terms of the physics that is realized in these calculations. And I should stress again, none of these affords enough resolution to resolve the accretion disk properly while affording to resolve stellar feedback. Not even talking about magnetic fields, not even talking about potential effects of dark matter annihilation, etc., etc. So the image that I think most people in this field would subscribe to now is that the primordial mass spectrum should be roughly logarithmic flat, which of course implies that for present-day standards it is top-heavy, or maybe a better expression is it is bottom-light. All right. So what about the transition to present-day star formation? Let's come back to the Omukai plot, because what we now need to do is we need to go and look at the other colors. So in particular, this is the present-day metallicity. This is something like the SMC metallicity. So this is really stuff nearby that we can look at and test. And it turns out that it has features. And these features are associated with two vastly different processes. Above metallicities of 10 to the minus 4-ish, 5-ish dust forms. We have dust, and we have all these goodies that dust does for us. And it needs to be pointed out that for star formation, the thing that dust does is A, it makes molecular hydrogen, but this is more a tracer thing, and B, it acts as a thermostat. Because eventually there is a certain level of the density where the gas particles collisionally couple with the dust particles. And you know that the dust opacity scales with the ambient, or in a sense that the associated thermal radiation field and the temperature scales with something like the 5th or 6th power. So if you invert it, if you change the radiation field by 1,000,000, the temperature of the dust only responds by a factor of 10-ish, maybe 20. So this is what I think we can, with good persuasion, call a thermostat. And then there are processes that are associated with line cooling, in particular with CO, C1, and C2, so fine structures. And it turns out that they are separated in the low metallicity case in the old universe, and they are kind of coming together at present days. And it has been suggested that the kink in the equation of state is responsible for the characteristic mass in the stellar spectrum, in the stellar mass spectrum, I should say. This goes back to Richard Larson in the 80s. And I think it needs to be said that, to me, this is truly the hero of star formation, and he was, like in many other cases, he was just right. So if you put such an equation of state into a simple fragmentation model, this is from his original publication, so quite a while ago, 40 years ago, and we put that on a computer, then what we get is, oops, very wrong direction. I have the same problems as you had. Then we can nicely reproduce the stellar mass spectrum. And the kink where these loitering phases, where the material cools down to sits for a while and then slowly lifts itself out again, we can read off a Jeans mass there because we have a density and a temperature. And within a factor of a few, maybe 20%, this is related to the characteristic mass in the resulting mass spectrum. And so we can, of course, do this in a much more sophisticated fashion. We can split the temperatures of the dust and the gas. And this is the primordial case, so no dust cooling, very little dust cooling here at the metallicity of -6. However, it becomes more and more important, and as predicted at number densities of this and masses of around 100th of a solar mass, the dust the gas gets thermally coupled to the dust. And if you look at the resulting mass spectrum, that is from Gustavo Dobke's work, then you see flat, 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 and you see a peaked IMF. Again, this is quite a while ago. There is much more recent and better studies by the Japanese group. This is from Omukai's group. This is Choyung Cho, who has done that. A very similar result. There is a transition of the resulting mass spectrum as you go from very low metallicities to somewhat more, bit more, and kind of SMC-type metallicities. So there is a characteristic change in the stellar mass spectrum. So as a quick interim summary, I think we understand roughly the mass spectrum. In the most simple approach, we understand roughly the transition from truly primordial star formation to something that more resembles what we see and know and taste and feel in the Milky Way. But the models are still super simple. In particular, we know from present-day star formation calculations, we need to take many other processes into account. Magnetic fields change the fragmentation behavior. In the context of radiation influences the fragmentation behavior in the disk. In the context of primordial stars, we also need to maybe think about what dark matter metal do we include. If it is self-interacting and annihilating, this produces heat. And it has been actually suggested there could be stars, so-called dark stars, that are simply powered by the annihilation energy release, the energy release from dark matter annihilation. So all this will reduce the degree of fragmentation, but we have other things that will increase it, like the streaming velocities. And I will come to that in a minute, but I think it might be useful or interesting to look at some of the properties of these standard population 3 stars. And so I compiled essentially what I could get from the Geneva evolutionary and stellar evolutionary tracks in a few figures of merit that I think are potentially useful if you model star formation in the early universe. So the first thing you notice is if you place these stars in a Hertzsprung-Russell diagram, then the colored stuff are the primordial stars, and this is just the main sequence for solar metallicity stars. So they have roughly the same luminosity, but they are hotter in temperature, and hence they are bluer. And that has a huge impact for the way we potentially observe these stars at the primordial universe and what influence they could have on subsequent star formation. What we can also then plot is the lifetimes. They are comparable in many ways to the lifetimes of present-day stars. Their luminosities, as I said, are also not that different. By the way, the symbol size is the big thing is main sequence, and then as we go on, this goes eventually off the main sequence. The surface temperatures are significantly hotter, so we get 100,000 Kelvin, which is quite a lot. And they tend to be very compact, and I'm also getting back to this. So this is in solar radius, and so they hardly reach 10 solar radius at maybe a few hundred solar masses. We can compare these, I skipped that. So we can put all that and compare what is their radiative output. And as I said, their overall luminosity is not that different to present-day stars. So I plot here as function of mass for different stellar populations. The fat blue stuff is primordial thing, and the red stuff is present-day, and there are few metallicities in between. So whereas the overall radiation here for the high mass stars is not that different, this is the Lyman-Werner band. This is the hydrogen ionizing number of photons, so above 13.6 electron volts. This is what ionizes helium, and this is what ionizes the already once ionized helium. And you can see, if we go to hard spectra, ionizing spectra, there is a huge difference by a factor of 10 or even more. So because they're more compact, because they're hotter, these stars have a much higher ionizing power than present-day stars. I put together that in an easy-to-use table. If you're interested in the details, maybe more interesting is the question, if I have one baryon per star, how many photons does it produce? And of course, in order to address that, you need to integrate over the stellar IMF. So for the population 1, I take a standard Krupa IMF. For the primordial one, I take the standard logarithmic flat IMF. And the total number of photons per baryon is not that different, but the difference arises if you talk about the ionizing. So this is hydrogen ionization. If you go to really helium ionization, then there is a huge difference. And that could be one way to identify the impact of these stars on the high redshift. You know there are these high redshift sources that show helium ionizing. And that could be a signpost of, or has been interpreted as one of the potential answers to explaining this as being the result of primordial stellar populations. So what I present here has been super simple once again. I take the stellar radius and the surface temperature, assume blackbody radiation, and out comes all I need to compute in terms of the spectrum. And one can immediately ask, is that true? And if I speak with someone who works on stellar atmospheres, he tells me, oh, you guys are naive. This is clearly not the case. And so there is work by people in the other Cambridge, Gessie Jones, who did that. And this is just a 6 solar mass POP3 star, roughly at the end of its main sequence lifetime. And the orange curve is the standard blackbody, and this is what comes out of a stellar atmosphere code. And you notice there are discrepancies, and particularly relevant are those when we talk about ionizing photons. So these things may not be so bright as I have predicted. And so in principle, one would need to repeat all of that with stellar populations that have proper stellar atmospheres. And I think that is still work that needs to be done, to a large degree at least. All right, in the last, 10, maybe 15 minutes, I try to address, Charlie, your puzzlement about these supermassive stars, which again I find is really interesting, and it is a side product of looking at the conditions of star formation in the primordial universe. So we can start with the simple genes argument, and we can ask, what do we need to do in order to get more mass, to get larger masses? And there are two ways. There is the density, but if you want to go to stellar densities, there is not that much Lie room there. And so we can look at the other thing that is here in the old genes analysis, the thermal sound speed. But we could think of, and many people in the present-day star formation community have done that. Chris McKee and others have been worked on that, basically following the footsteps of Chandrasekhar and von Weizsäcker from the 50s. One could say, but what happens if you have an effective sound speed? What happens if you have microturbulence that on the large scales of interest essentially acts like an additional thermal motion, an additional thermal pressure? What about highly tangled magnetic fields? Can't we just take the Alfvén velocity as a sound speed? And both have been done. And so, and both have been proposed to reach high mass stars at the present universe. And we can just make these more extreme and ask, does this give us leeway to form more massive stars in the primordial universe? So this brings me to the notion of the atomic cooling halo. So imagine you are in the primordial universe, you are pride owner of a halo that is already currently forming population 3 stars. You are radiating Lyman-Werner radiation, you are emitting ionizing photons, and then there is your neighbor who says, but I also want to form population 3 stars, but your radiation keeps me warm, it prevents me from cooling down, and so I can't. So what the neighbor does, he sits and accumulates more and more mass until he has so much that the gas he has accumulated, and we talk about millions of solar masses, roughly, instead of maybe 100,000 or a few 10,000s of solar masses in gas, to form stars. And so that has been postulated to happen quite in abundance. There is lots of literature how far your neighbor must be away, what the timing is, because when I have my tiny little first star, it only radiates for a few million years, and then it makes poof, and then it's gone. So in order to affect my neighbor, this needs to be somewhat contrived, but all these can be calculated. So this neighbor now has a huge gas reservoir that eventually goes into collapse. You can reach this in a different way. As has been shown, if you do second-order cosmic perturbation analysis, there is a relative streaming velocity between the dark matter component and the baryons. And so if you have baryons streaming with respect to the dark matter background, the interaction between the two can lead to small-scale turbulence. And you can then argue that you need to accumulate more mass to become gravitationally unstable, just simply by the virtue of the Jeans argument we have made before. You can put that on a computer. This has been done by Anna Schauer. And this sequence here shows no streaming velocity, so typically the cosmological model we all work on. 1 sigma, 2 sigma, quite a bit streaming velocity. And whereas this one happily forms a first stars, this one forms nothing, and here it takes a long time. You can combine this thing with that thing, and you can also look what is then the external irradiation. How does this come into play? And so this is the same sequence, but now with external irradiation. And again, star formation here, nothing here, nothing here. We can try to make sense. We can do a parameter study, and we can come up with a prescription of the minimum mass for gravitational collapse. So in principle, if you take this additional physics into account, you need to augment the simple cooling mass criterion and gravitational collapse mass criterion that I've shown you in the first 2 slides. So you need to augment Avi's original analysis of that problem. And this can be done here. Maybe it should be noted, or I found it, I asked Anna, well, you know, is this important or is it not important? What is a typical streaming velocity? And so it turns out that a streaming velocity of something like 0.8 of the RMS is what most of the halos are affected with. So there is some effect, but very little gas is influenced by these extreme relative velocities. All right, so let's go back to our halo. Let's say we have accumulated lots of mass, and we now go into collapse. And what happens is that as you go into collapse, you collisionally ionize parts of your atomic hydrogen. Now, you would think, why does this help me cooling? But now I have free electrons, and I have maybe a factor of 10, 20, or a bit more free electrons, and this catalyzes the rapid formation of H2. So super counterintuitively, as this atomic cooling halo collapses, it very rapidly goes molecular, has access to the cooling channels I've described before, and now you find yourself with many, many Jeans masses. You find yourself highly unstable, and under these conditions, there is exactly one thing the gas will do. It will fragment vigorously, as demonstrated in this by now somewhat dated calculation. So if you accumulate that in the atomic cooling halo, the large mass reservoir will help you to form supermassive stars, however you have fragmentation. So how can we reconcile that? So under these conditions, you are not forming roughly a flat IMF, but something that is actually top-heavy to some degree. Good. Then let us come to the question of what does stellar evolution tell me in this context? Because in the end, we need to form a star. And so we need to ask, what do the equations of stellar evolution tell me if I subject them to a high mass accretion rate? And so one of the things to mention in this context is you may always think of the old Schuh paper from 1977, who says the accretion rate is more or less 0.98 is the prefactor of the sound speed cube divided by the gravitational constant. However, this prefactor is where most of the physics is, because that makes the assumption nothing happens. I accumulate slowly gas, and suddenly I feel myself above the Jeans mass, and I go into collapse. But what happens if I will not go to 1 Jeans mass, but the gas is compressed heavily and has 10, 100 Jeans masses? Then this prefactor is not 1, it can go up to 50 or 100. So it is in the appendix of Schuh's paper, but it is usually neglected. So in order to make the supermassive stars, you need a situation where you go vastly, vastly beyond having just 1 Jeans mass available. So I come back to that. The question now is, what do stellar evolution tell me? So there are many stellar evolution models on the market. There is the Geneva model. There is MESA that can cope with mass load onto the surface. And it turns out that there is something like a critical mass load onto the stellar atmosphere, which is somewhere between 0.01 and 0.1 solar masses per year. Just for comparison, the highest accretion rate you will ever learn about in the Milky Way is maybe 10 to the minus 3 solar masses per year. So this is already a factor of 10 to 100 more. So it turns out that if you subject a star to such a heavy mass accretion rate, it is never able to reconfigure itself in such a way that there's an entropy wave moving through its surface and goes from a bloated high radius to a compact dense configuration. So these guys here, this is a standard stellar evolutionary or stellar model track where temperatures here, luminosities here, and in this thing, you can easily point or draw the lines of constant stellar radius. So 100 stellar radius, 10,000, 100,000. And so these stars that are subject to huge accretion rates are never going down to the path that I've mentioned before. And again, this is not something that is just visible in the Geneva code. It is visible in MESA if you use the Hosokawa stellar evolutionary model. This is a common feature of all these stellar evolutionary models. The stellar structure equations allow you, under the condition that you accrete at high rate, to be in a very puffed up configuration. these stars, you probably best to see them as red supergiants that are subjected to an enormous accretion flow, and that happily in their center burn hydrogen. And one can look at typically Kippenhahn diagrams. So the yellow stuff is hydrogen burning, so they have shell burning just like some of these giants. And you should look at the mass range. So usually in the solar neighborhood, you stop here. But if you somehow maintain this large accretion flow, here we have 10,000, here we have 1 million solar masses. And again, this is just from our own work, Lionel Hemmerle's work, but Hosokawa has very similar plots. And so this is, I think, well accepted in the stellar evolution, stellar community. And there is an interesting thing here where it turns red. And that is because you can ask, can this go on forever? And the answer is no, because eventually these stars get so extreme in their interior that the general relativistic instability sets in. That is an instability that first has been speculated about by Chandrasekhar, and the most recent very detailed analysis comes again from Hemmerle. And in principle, it is some kind of pulsational instability that takes the relativistic corrections in the necessary relativistic corrections in the interior of the stars into account. And then there's no escaping. The thing will start to oscillate and it will just whoosh, immediately collapse to a black hole after very few tiny little oscillations. So this is a runaway instability that is unavoidable. So now you may be confused. Because at one hand, I have shown you how can we make supermassive stars under these conditions. And we need two things. We need a huge accretion flow into the center of a halo. We need a huge mass. And both is available in these atomic cooling halos or their kinsmen driven by the streaming velocity and so on. On the other hand, I've said, if you have such a condition, there is no way this gas will continue in a regular fashion to one point. This is not a direct collapse. Such a situation will fragment, and it will fragment enormously and vigorously. So how can we reconcile these two questions? Let me skip that. Yeah, maybe one more thing. These stars, you can ask, they have 1 million, maybe 10 million solar masses. Shouldn't they just remove all the gas in their surrounding? The answer is no, because they are very red. Their surface temperature is somewhere 3,500, maybe 4,000 Kelvin. They will not produce much ionizing photons. They will be super bright in the infrared. So maybe there's some link to these luminous red dots that have been discussed in some of the previous colloquia. So they will have little impact. So in the remaining, oh yeah, now I really need to speed up 1 minute. I think the way out has been shown already by Martin Rees and Begelman and others. So because what happens if you have this fragmentation? The fragmentation leads to the formation of a super compact cluster of accreting stars. These stars will be very puffed up because they are subjected to large accretion rates. They have stellar densities that exceed that of, let's say, the Orion Nebula cluster by factors of 100 or 1,000 or more. And so there could be runaway collisions. And so I show you a calculation that has been done by a student in Heidelberg in collaboration with Dominique Schleicher in Concepcion, where we model both accretion and runaway collisions in such a compact configuration. And it turns out, when you do many, many of these calculations, you always have one object that runs away. And in this wimpy context, it gobbles up 80% of the mass. There is a cool side effect. So in many cases, it forms just a single runaway, but sometimes there is a binary, which could have potential implications for, let's say, space-borne gravitational wave experiments. Because this binary will do something, it will evolve, and it may be a potential target to future studies. We can look at how much comes from stellar collisions, how much comes from accretion. I will not bore you with that. But I think this is a way forward to get supermassive stars. You form then a cluster of stars that collide, that can stick together if they collide, and they can go into a runaway phase. And the question whether this bears any resemblance to the homogeneous accretion rate I've been describing before is now a question of how frequent are these collisions and how quickly does the star, the collision product, recover from this phase. Because what you do not want is that it comes in the compact configuration, blows away the gas, and decreases its collision rate. So that, I think, is, to me, the frontier of the supermassive star business. So if you manage to get these stars, as soon as you have the collision or accretion rate stop below the equivalent of 0.01 solar masses per year, the thing will just collapse into a black hole. And this could be the seeds then of the high-redshift quasars that we observe now in abundance. I have a postscriptum on observability. I will skip that, but I think there is very little pathway to see genuine population 3 stars with James Webb in the primordial universe. It's much more fruitful to do galactic archaeology and look at their imprint in terms of abundances on things we can really measure in detail in our backyard. And I think what is super exciting is now gravitational waves, because they give us access to the mass spectrum of the high mass end on the binarity and many other features. And with that, I come to an end. I put up 3 bullet points, which I think are the main conclusions. And thanks for listening.
Well, thank you very much for this very interesting talk. So if anybody has questions for Ralf, now's a good time. Josh?
Wonderful talk.
Thanks.
Wonderful talk, but I'm surprised you didn't mention gamma ray bursts. These massive stars will collapse, and our present understanding of gamma ray bursts, long gamma ray bursts as we used to call them, type 2 gamma ray bursts as we now should call them, as opposed to mergers, are going to be enormously luminous. And I'm mentioning all this because we are thinking about that here, and others are as well, to propose a mission that would detect these easily. And it's never been done, largely because we're never looking at enough sky. We have a concept that images the entire sky all the time, so you miss nothing. But has anybody in your group or others been working on this is really my question, because I think this is a very promising way to explore what happens to these massive stars.
I think this is a wonderful idea. Honestly, I'm almost totally ignorant about that. We have looked at X-ray binaries and the buildup of the X-ray background emission from primordial stars and very early population 2 stars. But I personally never have thought about gamma ray bursts in this context. But I think it is, as you point out, when these things collapse to form the black hole, this is super energetic event, there must be gamma rays released. And I think looking at the rates expected from these type of models would be interesting in your context. Thanks.
So as you know, there are several groups looking for POP3 stars in the in the Milky Way.
Yes.
These low mass remnants. If we do or don't find any, do you think it will actually be very constraining on the models?
Yes.
What would we learn if we found some some 0.7 solar mass POP3 stars?
Yeah. So you raise an important point that I have completely taken out of the talk. I mean, the prediction of these dynamic models is there must be genuine low mass population, 3 stars, and if they have gone down to 0.7, 0.8 solar masses, they should remain in the Milky Way until the present days. These models, ours and many others, predict 10,000, a few 10,000s of the stars, mostly in the bulge, some in the halo. There are a number of papers from our group, Mack et al., Hartwig et al., looking where we would best find them. Our prediction is if you look at some of the ultra-faint satellites, your chances are best if they are there. And there's also Stefania Salvadori's group, also with Raffaella Schneider, who have done lots of work on this. And they also have a semi-analytic model, just like us, to make predictions of the rates and the numbers and the expectations for various observations. To me, the conclusion is we are almost there to rule out the low mass, to constrain the low mass end of the population 3 IMF. I think if we double or tenfold the current sample size, which is in easy reach and will happen in 1 or 2 years timescale, and we still have not found one, and we still cannot come up with a good way to pollute these stars by cruising through the Milky Way and gobbling up ISM material, then I think we can constrain these models, which would be bad because in a sense, my model, we have been working hard to advocate the existence of low mass and surviving population 3 stars. But on the other hand, we have learned something, which would be rather cool. So I think this is a key pathway forward. I fully agree.
Fascinating talk, Ralf, as always. But if we look at regions that we can observe today, which are forming very massive stars, there always seems to be a huge amount of feedback from the forming stars or the process of forming stars.
Yes.
In the form of supernova explosions or radiative heating or winds that tend to blow away gas and kind of self-limit the global inward accretion that you're talking about.
Yes.
And so is this something that we should expect under the extreme conditions that you're talking about, or is it somehow possible to suppress all of those effects?
So this is, I think, a key question. And in order to answer it, we need to distinguish between what I would call the standard pathway to population 3 star formation, that was the fragmentation in the disk in the standard halo, and as opposed to this pathway to the supermassive star. So for the first one, I fully agree with you. These guys will be very compact. I've shown you the radius. We talk about a few solar radii for 50 solar mass star. Temperatures are 35, 40,000 Kelvin. This guy will be a super bright in UV, and it will ionize its surrounding. Now, what impact this has on its own mass flow is still subject to debate, because you need to resolve the scale height of the accretion disk. So if you do that, then at least we think exactly that happens what you, Eric, have been predicted for many years. The accretion flow, despite being ionized, could be quenched and pushed back. And so the H2 region will not break out, and it is largely the dynamics of the environment accreting material on the disk fragmenting, the interplay of its spiral arms that regulate the mass growth and the distribution of this mass onto several objects. That is, I would say, very similar to present-day star formation. In this primordial case, in this more extreme case, the key question is, do you keep these stars in the puffed up red phase? As soon as the radius drops, temperature rises by a factor of 10, 50, we have lots of ionizing photons. But as soon as, or as long as you have a star that has 10,000 solar radii, has a surface temperature of 4,500 Kelvin, it will not ionize much. So it will only do lots of infrared radiation, or maybe extremely red radiation, but it will not influence much the gas. And so the key is in the timing. And there is another thing that worries me quite a bit, which I have not talked at all about. In this collisional runaway, we always say if you have two stars colliding, this is mostly sticky. But then the recent calculations that the people at Geneva Observatory do, you can simply do the exercise, take a 10 to the 4 solar mass star and shoot in a 1 solar mass star. This star has the potential to unbind 30, 40% of the outer layers of the star in terms of mass. So it is not at all given that collisions will always lead to the runaway mass growth. They could be rather self-regulating. But that is a completely different thing and is absolutely unexplored territory, because you need to update the stellar evolution models. You need to be informed about the orbital elements of the encounter, etc., etc. And no one has done that really consistently.
So in the present-day universe of star formation, most of the energy in the molecular clouds is in the form of turbulence. And so these calculations like Larson did, which give you a kink in the equation of state, are based on the thermal energy, right?
Yes.
The cooling, right? And so what I would say in the present-day universe is that one has to deal with the thermodynamics of the turbulence itself and not the thermodynamics with respect to the thermal energy of the gas. And then in the primordial universe, you have sort of the same thing, right? You set the problem up one way with the cooling by lines and dust or whatever, and then you end up with lower mass stars. Then you throw in, say, an effective sound speed, which is due to the turbulence, and you get these much more massive stars. So what do we know about the thermodynamics of the turbulence in the primordial universe?
So we looked at that question quite extensively. And the first thing to notice is that the turbulence in present-day molecular clouds is highly supersonic. We know and it is the dust cooling that keeps these clouds at low temperatures, 10, 20 Kelvin. So isothermal turbulence, an isothermal shock leads to density excursions that are quadratic within Mach number. So if you have, let's say, an RMS Mach number of 10, you expect density of excursions easily of 100 and a distribution around it. The turbulence in these conditions in the early universe, in these collapsing halos, is subsonic. And they happen on a strongly contracting background in the first place. It is still enough by the virtue of the small-scale dynamos. So if one follows the work by Shikushihin or Subramanian and Brandenburg to bring the magnetic fields up to saturation level. But the magnetic fields will be, from this process, small-scaled and probably saturating at 10% of the dynamic value. So the turbulence also has maybe a Mach of 0.5, give or take. So this effect does not do much. It is indeed, in essentially all the calculations that take the environment into account, the fragmentation of the disk, its ability or inability to cope with the mass load it receives from the larger scale environment that sets the scales and the time scales here.
Well, let me ask the last quick question.
Yes.
I was a little confused by the end of the talk.
All right.
Are you proposing or saying that there are two pathways to supermassive black holes? One, you have this 1,000,000 or 100,000 solar mass star-like object, and then somehow the accretion stops and goes into a black hole. And in the other case, you have a cluster of 10 to the 4 solar mass objects that are very tight, and through collisions go into a black hole. So are these two pathways you're looking at, or is it?
So I think the first pathway, the old Rees picture of the direct collapse black hole and there's the stellar phase in between, is not working because fragmentation seems unavoidable. Then the question is, maybe it doesn't really matter, because if you have the fragmentation, the star cluster is super dense, the stars are very large, you have enormous collision rates and frequencies. So there are 20, 30 papers on various aspects of these overall problems. And most of them, essentially all of them, come to the conclusion there must be something like runaway accretion. So I think in the end, fragmentation is not a problem because we can get around it through the back door by runaway collisions. They just need to happen frequently enough such that the star cannot compactify itself over the Kelvin-Helmholtz timescale. So it depends on the detail. But I'm convinced if you really do the statistics as needs to be done with simulations and looking at the conditions of the various halos from large-scale simulations, as also done here in this institute, then we get roughly the right rates to explain some of the supermassive black holes in the primordial universe.
All right, well, let's thank our speaker for an interesting talk.
Nice to meet you.